Okay, so this class will be talking about invertible operators. So let's start with a definition. So definition, so let's say that we have t, which is a bounded operator going from x to y, is invertible if there exists s in b of yx such that s times t is the identity in x and t times s is the identity in y. Okay, so this is what you would call the left inverse, and this is what you would call a right inverse. Okay, so this is left inverse and right inverse. Okay, so just to give you an idea, of when these things could not actually be the same. So let's take the example that we have done before, which is the shift operator. That goes, let's call it t, that goes from little l2 to little l2, and this sends t of x1, x2, so on to 0, x1, x2, so on. Okay, so this mapping is actually not invertible, but it has what I would call a left inverse. Okay, so if we take s of x1, x2 to be x2, x3, and so on, then s is a left inverse for t, but not a right inverse. Okay, so yeah, one has to be a little careful with this. So you can have left inverse and right inverse for t if you are looking at the image of t. So if you restrict yourself at all the sequences that have a 0 for their first element, then you can actually check that s is a left inverse and right inverse. Okay. Anyways, let's look at a quick lemma of these things. So what is the lemma? So let's say that we have x, which is going by t1 onto y and by t2 onto c, such that t1 and t2 are invertible. T1 and t2 are invertible. Okay, then what are the properties? T1 inverse is also invertible. Is invertible with inverse T1. Okay, so I didn't say this. T and bxi is invertible if there exists s that is going b, y, or x. So s is called the inverse of t. It's called the inverse of t and is denoted by t inverse. Okay, so t inverse is also invertible with the inverse, which is just t itself. And then the next one is that t2 composed with t1, which, as we said last class, we're going to denote by the product, is invertible with inverse t1 inverse t2 inverse. Okay, so this is t2 inverse, which is going from c to y, and this is t1 inverse, going from y to x. Okay, so if we take the composition T1 and then T2, then the inverse is going to be T2 inverse and then composed with T1 inverse. Okay, so the proof is the same as for matrices. So it's the same as for matrices. What do I mean? Like whenever we have, so instead of looking at linear operators in infinite dimensional spaces, this is similar to looking at AX is equal to Y, then if determinant of A is different from 0, and so A here has to be a square matrix. If determinant of A is different from 0, then exists A inverse, and then the same thing, A times B inverse is going to be B inverse times A inverse. Okay. So what are, I guess just to bombard you a little bit with notation. So anyways, in terms of these inverses of things and this kind of stuff, I would say to think of them as if they were matrices. Okay, so if there is something you can do for matrices, there is something you will be able to do for these operators at least. The question that we're going to be addressing a little bit is what is similar to this determinant of A different from 0, which is basically saying that all of the columns of A are linearly independent, and also what is the concept of square matrix in the infinite dimensional case. Okay, so let's take a definition. So X and Y are normed linear spaces if there exists T in B of xy invertible, then x comma y are isomorphic. Okay, so this is the definition. If there exists a T that is going from x to y invertible, then what we're going to say is that x and y are isomorphic, and T is an isomorphism. So what is the point of this? So if we, like, the fact that its spaces are isomorphic will actually have a lot of, mean that the structure of X and the structure of Y has to be fairly related to each other, okay? So this is the notion of equivalence in terms of linear subspaces, topological linear subspaces. So one of the properties would be if dimension of X is finite, then dimension of X is equal to dimension of Y. Okay, so and this is something you should have seen from linear algebra. If you have an operator T that is going from Rn onto V, which is just a some vector space, then and exists the inverse going from V to Rn, then V is isomorphic to Rn, and then this implies dimension of V is equal to 1. Okay, so these are for finite dimensional things that you should be used to. But now these are like more of the properties we'll be talking about. So if X is separable, if and only if Y is separable, and X is complete, if and only if Y is complete. So how do you show this? And I'm not going to show them right now. This has to do with topological properties. Okay, so two spaces have the same topological properties if they are homeomorphic to each other. So isomorphic spaces are homeomorphic, which implies point set topology invariance. Okay, so separability is a concept of point set topology that is preserved by homeomorphism, and completeness is also something that is preserved by homeomorphisms. Okay, so these are necessary conditions, but they are not sufficient. So these are necessary conditions. Which are far from being sufficient. Okay, far. All right, so let's look at a case that is easy to check if something has an inverse or not. So morally, what we are after in this next couple of talks, in this class, is how do we generalize this determinant of A different from 0 in the way of matrices to get the fact that there exists an inverse. Okay, and this will be the open mapping theorem. But before we get into something which is that abstract, let's try to do something which is a bit more common ground, let's call it. So let's look at the following theorem. Let X be a Banach space and T is in Bx such that the norm of T in the space Bx is less than 1, then I minus T is invertible, and let's call it I minus T. So, okay, let's put it like this. I minus T inverse is equal to the sum from n equals to 0 up to infinity of T to the n. Okay, so this is bad notation. Okay, so this is non-standard notation. It just makes me realize what this I minus T inverse is. It's like 1 over I minus T. But, okay, so what is the heuristics for this? Um, 1 over 1 minus x is an analytic function, with radius of convergence are less than 1. Okay? So in particular, so by analytic function, it just means that 1 over 1 minus x is exactly equal to the integral to the sum from n equals to 0 up to infinity of x to the n. Okay, so we can write this as this sum for every x which has modulus less than 1. Okay, so this guy is an analytic function. So then what we are doing here is we're looking at the function 1 over I minus t, which can be written as the sum of these guys. And this is similar to what I said before in the previous class. So this is similar to taking E of t, which is equal to the sum of t to the I factorial. So the point is, if you have an analytic function, you can actually write it in its power series for an operator. So we can use power series. Okay, and what is the nice thing about so e to the t, this has a radius of convergence. So the radius of convergence is plus infinity. Okay, so this e to the t can always be defined. Okay, so now the point is, this is the concept that is behind this theorem. So whenever you're taking something which is 1 over something, if you can write it as a power series, then in the radius of convergence, you will actually be able to write it as the power sum. Okay. So let's look at the proof of this. So proof of this, let's start with the first observation. If x is Banach, then by last class, b of x, which is the bounded linear operators from x to x, is also Banach. Okay, so what we're going to show, that the sum from n equals to 0 up to k of t n, which we are going to call sk, is a Cauchy sequence. Okay, so we take sk1 minus sk2 in norm, and this is equal to the sum from n equals to k1 up to k2 of t to the n in norm, which is less or equal than the sum from n, let's say from k1. So here I'm assuming k1 less than k2 without any loss of generality. So this is n to k1 up to infinity, and the norm of t to the n. So here I've used it in triangle inequality. And this in term is also less or equal, and this is by last class. The norm of t to the n is actually less or equal than the norm of t to the n. Okay, but this can be made arbitrarily small. This can be made arbitrarily small as the norm of t is strictly less than 1. Okay? So using that this is a convergence series, we can actually show that this guy is a Cauchy sequence, because if we take k1 large enough, so when k1 goes to infinity, this guy goes to 0. Okay, so this is a Cauchy sequence. Then there exists S such that sk converges to S, and I mean, we are just denoting this as the limit of the series, which is equal to n equals to 0 up to infinity t to the n. Okay, so the next property that we need to show is that S is the inverse of I minus t. So the next claim is that S is the inverse of I minus t. And so the way that we're going to do it is by passing through the limit using the sk. So what we're going to use is, okay, so we're going to compute I minus t applied times sk. But this sk is just the sum of t to the n up to k. So this is going to be, so multiplying inside a finite amount of terms, this is the sum from n equals to 0 up to k of t to the n minus, and now when I multiply by t, you get t to the n plus 1. So this is actually equal, and this is just because this is a telescopic sum, that this is actually equal to identity minus t to the k plus 1. Okay, so in particular, I minus t times sk is a small perturbation of the identity. Okay, so what we can check is that if we take identity minus I minus t times sk, and we take the norm of this is going to be equal to the norm of t k plus 1, which in terms, this is less or equal, and this is again by last class, of the norm of t to the k plus 1, which goes to 0 as k goes to infinity. Okay, so what we have just shown is that the limit when k goes to infinity of identity minus t times sk is equal to identity. But last class we showed that composition of operators is continuous under convergence. Therefore, we can distribute this limit in each of the pieces. So we can distribute the limit when k goes to infinity in I minus t, and we can distribute the limit k goes to infinity in sk. And so then what we have is that I minus t times the limit and k goes to infinity of sk is the same as the limit outside I minus t times sk, which in turn is equal to I minus t times s, which is equal to the identity. Okay, so here we've shown that s is a right inverse for I minus t, and the same argument shows s is a left inverse. Then I minus t minus 1 is equal to s. Okay, so that's the proof of this. And let's look at a quick application. So I guess a couple of comments here. So in a sense, I mean, this is just telling you if you have an operator which has norm strictly less than 1, then you can take I minus the minus t and actually get that this guy is invertible. Okay, so this is the statement of the proof, statement of this. So this guy is used in a couple of things. So in particular for okay, so let's look at an example or application. And let's call this solution to convolutional equations. And these sometimes are called non-local. Okay, and I'll show what we call by non-local. So let's say that we want a solution to the following problem. G of x is equal to f of x plus the convolution of k with g at x. Okay, so now we have an operator which we're going to call capital K that is going from L2 to L2, and here we'll just consider L2 of R. So, so we have this operator K such that Kg at x is just given by the convolution of this little k, so this is going to be the integral over R of k of x minus y, g of y, dy. Okay, so for k to be bounded in L2, and this is something that has to do with the exercise I've shown before, is that k is bounded. So yeah, just this is capital K. Let's put it something like this. K is bounded, is a bounded operator if little k is in L infinity and the norm of capital K is equal to little k in L infinity. So then we can rewrite this convolution equation. So this convolution equation pops up a lot of times in terms of solutions of PDEs. So this k usually is the fundamental solution to a particular PDE. So you could think of this k as the Green's function for the Laplacian. Okay, so this is something that Laplacian of k is equal to the delta at 0. Something along these lines could be the type of thing that we're trying to do. So in this case, we can write this as G minus the operator K applied to G is equal to F. But this thing is just the identity minus the operator K applied to G is equal to F. So then, if the norm of K is less than 1, then there exists a unique G solution to the convolutional equation, and is given by G is equal to the sum from n equals to 0 up to infinity of k to the n applied to f. So this is so k squared applied to f is just k little k convolution k convolution f. So k n of f is just little k convolution k convolution k to k convolution f, and this thing is done n times. Okay? So actually, you can actually show that there exists a unique solution G to this equation, and it's actually given by this. And the only thing that you need to check is that this function K in L infinity is less or equal than 1, less than 1. That's actually enough to find a solution to this. This is fairly useful. I mean, even in ODEs, some of these things are used. The way that, the Picard-Lindelof theorem is done is not so far from this. So, yeah, morally, the Picard-Lindelof theorem, you are using something on the order to show the convergence. Okay, so what is the corollary of the following, of the previous theorem? So what is the corollary of the previous theorem is let x comma y be Banach spaces. Actually, let's just say let x be a Banach space. The set of invertible operators is open. Okay, so what I'm saying is, basically what I'm saying will be clear in the proof. So we take the set of invertible operators, and I think in the book they define it as the set A. So A is equal to the T's in Bx such that T inverse exists. So there exists T inverse in Bx. Okay, so now what we're going to say, we are going to pick T in A, and we are going to show that there exists eta positive such that the ball of radius eta around T is contained in A. Okay, so this ball of radius eta contained in T is considered in terms of the norm, the metric in the algebra of operators. Okay, so that was what we took eta, so this eta can depend on T. So we choose eta, we pick eta, which is equal to the norm of T inverse, so 1 over the norm of T inverse. Okay, so now we need to show that if we need to show that if T minus S is less than eta, then S is invertible. Okay, so that's what we want to show next. Okay, so what we are going to check is the following. So we're considering T minus S times T inverse. And we're considering the norm of this. So what we want to show is that this guy is actually invertible. And how do we show this? We show that this is less or equal by the last class, what we proved last class. So what did we prove last class? We proved that the norm of a composition is less or equal than the product of the norms, T minus S norm times T inverse norm. But this guy is T minus S is less than eta, by assumption times T inverse. But we took eta to be equal to 1 over the norm of T inverse. So this guy is equal to 1. Therefore, by the previous theorem, T minus S times T inverse, which is equal to I minus S T, so by the previous theorem, what we get is identity minus what we have just written is invertible. Okay. Then, so identity minus T minus S times T inverse. This is when you multiply T by T inverse, you get an identity, and then you have plus S T inverse. So this identity cancels with this. So S times T inverse is invertible. Okay, but the other thing that we've shown at the beginning of the class, is the following lemma. If T1 and T2 are invertible, then T2 times T1 is invertible with inverse T1 inverse T2 inverse. So in particular, ST inverse is invertible, and using that T is invertible, then ST inverse times T, which is equal to S, is also invertible. Okay, and this is exactly what we need to do. So this is just the point that we start with this. This is just an ingenious way of then starting to pick off all of the things until you just get S as your invertible operator. So I think one of the main points is that you should remember is that the radius of invertibility has to do with the norm of the inverse operator. Okay, so the larger the norm of the inverse operator, the smaller the ball around that you can actually invert. Okay, so if you have something whose inverse is really big, then you have a really tiny ball around your operator, which actually is still invertible. Okay, so we talked a bit about like generalities of invertible operators. So like what is the inverse of a product, and how can we use some of these properties to show some cute little things. But the main theorem of this chapter is the following. This is called the open mapping theorem. And I think this is like, this is one of the main results of functional analysis. So what does the open mapping theorem says? If x, y are Banach, and you can actually reduce this condition a bit. If x and y are Banach, T is a bounded operator going from x and y such that T is surjective, then the image of T of B1 of x, which is the T of x such that x is B1, is open. Okay, so in general, I mean, I think open mapping theorem, one should be a bit more careful in saying, so what does open mapping theorem mean? Is that if T is surjective, T is an open map. If so, I say, in other words, if T is surjective, then T is an open map. That is to say, T of U is open for any U contained in X, which is open. Okay. So now this is a bit more complicated in the way that we're saying, but this is equivalent to what I'm saying here. So if you take just the unit ball, this being open is equivalent to any the image of any U being open, because you can write this as a bunch of union of open sets, and the linearity of T makes that if this thing is open, then any multiplication R times B1 of X is still an open set. Okay, so and then you can use translations and this thing to actually get that everything is open. So the only thing that you need to show is that T of B1 of X is open. And the only thing that you need to actually show is that T B1 of X contains a neighborhood of the origin at Y. Okay, we'll do this in the proof. Okay, but the main point of this theorem, and actually the theorem itself, it looks a little like abstract, but the main point is the following, which is fairly surprising, which is the corollary of this, that if T is injective, if T is also injective, then T is invertible. Okay, so let's rewrite this a little bit. What does this corollary say? We can call it theorem. So T is in B of X, Y. T is injective and surjective. Then, so T is bijective, basically. Then there exists T inverse in B of Yx. Okay, so it's a really like powerful thing. So if you have something that is injective and surjective, which is bounded, then it's invertible. So if you can find a bounded linear map from X to Y, which is bijective, then the two spaces are isomorphic. Okay, and this is fairly strong. So this is something you expect in finite dimensions, but in infinite dimensions it's surprising. Okay, so in finite dimensions, if you have something that is injective and it's surjective, this is the same as saying that the determinant is different from zero. In this case, there is not a notion of determinant, but there is this notion of bijectivity. So bijectivity plus boundedness is what implies that you have a bounded inverse. Okay, so first let's prove the corollary. The proof of the open mapping theorem is a bit more of a mess, and I'll do it at the end. But let's try to do the corollary, which is, I think, easier. Proof of the corollary. Okay, so T is bijective and linear. Therefore, there exists T inverse, which is going from Y to X, which is linear. Okay, so here the point is we don't know if T inverse is bounded. Okay, so, but we are going to use the open mapping theorem to say that if T is bijective, so then by the open mapping theorem. So let's start with the following realization. The 0 in y is in T of B1 x. Okay, and this is because T of 0x is equal to 0y, and this is just by linearity. So by the open mapping theorem, there exists a neighborhood of 0y, so which is, let's just call it B y r. Okay, so this is the ball of radius r positive around 0y. This guy is contained in the image of B1 of x, which now, using this bijective, this map T minus 1 inverse, this implies that the image of B r y is contained in B1x. Okay, so this is mapping one ball around the origin to a ball around the origin of x. My claim is this is enough. This is enough to show the inverse is bounded. Okay, and this is just a matter of like looking at the definition of bounded and playing a bit with it. Okay, so what is the norm of T inverse? The norm of T inverse is the supremum, let's say, of z in B1 of y of the norm of T inverse of c. Okay, and this is the norm in x. But now, what do we have from this property right here? We have that the sup of y in BR y of T inverse of y in norm has to be less than 1, because the image of BRY is contained in B1x. So all of these guys are in B1x. Hence, the supremum of the norm of all of them has to be less than 1, because the norm of all of them is bounded by 1. So the supremum is less or equal to 1. Okay, so the norm is less or equal to 1. Okay, but now I just need to transform from the ball of radius r into the ball of radius 1. So what do I do? So we can just use the linearity to say z of B1I of T inverse z. Let's take norm. And now let's multiply this by r. And then if we multiply this by r, then using the properties of the operator, so I multiply by r and divide by r. So then using the property of linearity of T inverse and using the properties of the norm, this is just 1 over r times so there is a 1 over r outside, times the supremum of y in BRY of T inverse of y in norm, because I multiply c times r. If z is in the ball of radius 1 of y, c times r is in the ball of radius r, little r. But in particular, by this property here, we have that this is less or equal than 1 over r. Okay, so, but this is just the norm of T inverse. So this implies T inverse is bounded. Okay, so the point of the open mapping theorem is a neat way of showing that the inverse is bounded. Okay, so checking this boundedness is good. It's good to actually just check that the mapping T is open. Okay, so let's go to the proof of the open mapping theorem. Okay, and this is going to take a couple of stages. The first thing is something that is usually referred to bare category theorem. I'm not going to talk about categories, so we just could call it bare category theorem. And the point is the following: a complete metric space is not the countable union of closed sets with empty interior. Okay, so closed sets with empty interior, these guys are usually called meager sets. So meager means something that is really thin. Okay, so it's something that is really, really thin. It's just a closed set which has empty interior. So a way to show this, and yeah, so this is if and only if. So let's call this UI. If so, this is if and only if. Well, it's not quite if and only if, but anyways, if X is a complete metric space and UI from I equals to 1 up to infinity satisfy UI open and dense, then the intersection from I equals to 1 up to infinity of UI is dense. Okay, so let's first show, so this would be the theorem. So the theorem is if X is a complete metric space and UI satisfy UI open and dense, then the intersection of UI is also dense. This actually implies that X, so let's consider, let's take AI closed and AI interior is equal to the empty set for every I. Okay, so this is I in N. Then X is different from the union of I equals to 1 up to infinity of AI. Okay, so this statement is basically saying this. So if we have a complete metric space, a complete metric space is not a countable union of closed sets with empty interior. Okay, so we take a sequence of closed sets with empty interior, then X is not equal to the union all of these guys. Okay, and let's show that this follows that directly from this theorem, because let's take AI complement is equal to UI. Now, UI is clearly, UI is open because AI is closed. UI is open and AI is closed. And then UI is dense because AI interior, the interior of AI, is equal to the empty set. So if UI is not dense, this implies that the interior is not empty. Okay, so this shows, and then by theorem, so the union, the complement of I equals to 1 up to infinity of this is equal to the intersection of I equals to 1 up to infinity of AI complement, which is what I've been calling UI, and this is different from the empty set because by theorem this is dense. Okay, and so X is equal to the union of AI if and only if the complement of this union is the empty set. But in this case, this cannot be just because of the theorem, this Baire category theorem. Okay, so Baire basically it's called category theorem because you talk about things that are first category or second category. So first category are all the things that can be written as the union of closed sets with empty interior, and second category are all the things that cannot be written like this. Okay, so a complete metric space cannot be written as a countable union of closed sets with empty interior. Okay, so let's prove. Anyways, so we're going to be using this for the open mapping theorem. So it seems a little roundabout, but it's the main point of that we need to use in the open mapping theorem. So let's now do the proof of the Baire theorem. So we are going to show that the intersection of UI is dense in the hard way. So take W contained in X an arbitrary open set. We will show that for every I in N, there exists, so that there exists XW such that XW is in W and XW is in UI for every I in N. Okay, so the way that you show density is that you can find a point for every arbitrary open set, we can find a point in W which is also in the set intersection of UI. So this is XW is in UI for every I, which is this is if and only if X of W is in the intersection I equals to 1 up to infinity of UI. Okay, so if we can show this, we have shown the theorem. All right, so how are we going to find XW? We are going to find XW by taking a progressive sequence. By taking a sequence xn, n equals to 1 up to infinity, and taking a limit. Okay, so what do we know? We know, so one of the hypotheses is that UI is open and dense. So U1 is open and dense implies, so UI is open and dense and W open implies that there exists an X1 which is in W intersection U1. So there exists an X1 in W intersection U1, and let's call it R1, which in this case we'll just ask that is less than 1, such that the ball of radius x1 R1 is contained in W intersection U1. Okay, so this is just using the property of U1 being dense, and then using the intersection of W U1 is open. So if you have a point W intersection U1, then you can take a little R1 in which you can do these things. Okay, so usually, I mean, the point is that here you need to put the closure. Let's try not to complicate ourselves too much by that. So let's, the next thing that we are going to say is that then, okay, so now this is an open set. This is an open set. Hence, then there exists x2, which is in B of x1 R1 intersection U2, such that and R2, which in this case we are going to ask to be less than 1/2, and R2, which is less than 1/2, such that x2, the ball center at x2 of radius R2, is contained in the ball of x1 radius R1 intersection U2. And so now if you follow this guy, so B of x1 R1 is contained in W intersection U1 intersection U2. Okay, so the point is that we are constructing this progressive sequence x1, x2, x3, x4, xn in such a way that these balls are always contained in the intersection of all of this. Okay, so now the point is to do this inductively. So, and this is a little funny, but to be able to do this, we need to use a weak version of the axiom of choice. So by axiom of choice, we can pick xn Rn. We can pick xn and Rn less than 1/n, such that the ball of xn Rn is always contained in B of xn minus 1 Rn minus 1 intersection Un. Okay, so you need the axiom of choice because now you have an infinite number of balls, and then you have to be taking a point. So you have to make sure you are able to take a point in each one of the balls. Okay, so that's why we actually need the axiom of choice. But this is not the axiom of choice for infinite things. This is just the axiom of choice for countable choices. Okay. Anyways, so what do we need to show here? So what do we need to show here? We need to show now that, okay, so now we have this sequence xn. We have the sequence xn. So the question is, does xn converge? And the answer is yes, because by the choice of Rn less than 1 over n implies xn is a Cauchy sequence. So why does imply that this is a Cauchy sequence? So because let's take the distance between, so let's take the norm between xn minus xm. And my claim is that this is less or equal than the max between 1 over n and 1 over m. Okay, and this is strictly less. So why is this? Because like if n is smaller than m, then by construction the construction xm is in the ball of xn with radius Rn. Okay, so because the construction is we always take the next xn in the ball of the previous element. So b of xn Rn is contained in the ball of the previous element, xn minus 1, Rn minus 1. So, but in particular, this Rn is less than 1 over n. So this implies that xm minus xn is less than 1 over n. So here I assume that n is less than m, and you can flip them the other way, and then you get these estimates. And this implies xn n equals to 1 up to infinity is a Cauchy sequence. Okay? Then, by completeness, there exists by completeness, there exists xw such that xn converges to xw. And now what we have to check is xw is in w intersection u1, so intersection u1, intersection u2, intersection u3, and so on. So xw is in w, in u1, in u2, in u3, in u4. Okay, so now we have to be a little careful to check that xw is satisfying all of this. So the idea is this should be, the answer is this should follow, this follows from the construction. Okay, but we need to be a little careful. Be a little careful. So why do I need to be a little careful is because, okay, so what we know is that xn is going to be in the ball of radius x, x1, r1, which is contained in w intersection u1. But now if we take the limit of elements inside this ball, they are not necessarily going to be inside this ball. Okay, so then usually, so there is a couple of ways of doing this. One of the ways is by taking the closure in each one of these things, and another one is just by saying, okay, well then there exists x2 in the ball divided by half. Okay, and now the ball of x2 r2 is divided by this thing, and here instead of taking b of xn1 rn minus 1, I take divided by 2. So the same construction follows. You can do the same thing, but then what we imply is that so what we have is that xn, so what we imply is that xw is in the closure of the ball of radius, ball of xn of radius rn over 2 closure, which is contained in the ball of radius xn rn, which in turn is in un. Okay, so then xw is in un for every n, and xw is in w because of the first step. So I'm not sure I can do a good drawing of this. So let's say we have w here, and then we have something u, which is we have an open u which is dense. So basically you have u1, which is everything outside of here. So then what we take is an x1 here and a little ball. So basically this thing here, all of this thing here is u1. So now we take a u1, so here we take x1 and this little ball of radius r1. Now this picture I drew for w, I can redraw for this ball. And now I can take u2, which is again an open set except a couple of things. So again, this is u2. And now what I'm going to take is an x2 inside here, which are radius r2, and this is x2. And then again, I sort of zoom out here. I look at what's happening in this ball. I have a u3, I create an x3, and so on. And then the point is this thing here, this zooming out, is going to happen again like x2, r2, and again you have a u3, and now you take another one. But these things, if you start, if you take it back to the original picture, are little balls, smaller and smaller and smaller, which are clearly contained in W, clearly contained in U1, but this is the same picture done iteratively, so it will also be contained in U2, it also be contained in U3, and so on. Anyways, so this is the proof of the Baire category theorem, and this takes us to the proof of the open mapping theorem. Okay, let me stop for 1 second.